Good morning. I'm John Yembrick at NASA Public Affairs, and welcome to NASA's Ames Research Center in Moffett Field, California. We're here today to announce some exciting new discoveries for NASA's Kepler mission, which is managed here at NASA Ames. Before we get started, I'd like to just make a quick reminder to those on the telephone that there could be a slight disruption. There's a sound that goes off here, a compression system. If you hear it, don't get alarmed, or there's nothing wrong with your line. We'll get started as soon as it ends. It typically lasts about 60 to 90 seconds. To give us an introduction to today's briefing is the Ames Center Director, Pete Worden. Dr. Worden.
Good morning. I'm very proud to have the Kepler team here at Ames Research Center, where we're hosting the first Kepler Science Conference beginning in just 30 minutes. Today, we'll hear about another major milestone on the journey to finding Earth's twin. Today's discovery is a tantalizing indication that with time, Kepler may find true Earth analogs, if they exist. We're getting closer and closer to discovering the so-called Goldilocks planet that is both Earth-like and in the habitable zone. Not too long ago, in the course of human history, we didn't even know there were other planets outside our solar system. Even in my own lifetime, we didn't know that. It wasn't even all that long ago that we didn't know that the Earth was the center of the universe. Now we know that planets are abundant in our galaxy. One could conclude that they're likely abundant in the universe. There are practically limitless discoveries, and Kepler is making giant leaps in helping us understand our place in the universe. Kepler just reached another milestone, 1,000 days since launch. The discoveries you hear today are very intriguing and reflect on Kepler's great potential. We've announced 1,235 planet candidates in February, and we're increasing that number today in confirming an exciting new discovery. All this reflects on a dedicated professional team and a harbinger of even bigger discoveries yet to come from the mission. Now, is a very special kind of treat, I think, for me. I'd like to introduce briefly the third director of NASA Ames Research Center, Dr. Hans Mark. I'm the 10th director. Dr. Mark has been my mentor. He went on to become the Secretary of the Air Force, the Deputy NASA Administrator, the Director of Defense Research and Engineering, and the Chancellor of the University of Texas System. But he was there when the first studies were beginning to be done on finding planets. So I'd like to ask Dr. Mark just to take a minute or two and tell you about the past as we're thinking about the exciting future. Dr. Mark?
Thank you very much, Pete, for inviting me here. I came back from the dead to be here. You need to understand that. Hi, Jill. Just a short point. We started to speculate about the existence of planets around other stars in 1971, in the summer of 1971, when we conducted a study here at Ames on how we would go about finding these planets. And of course, one way was to assume there were people on them and that they were sending signals out. And so this was called the Cyclops study. It was the first one. I remember raising $75,000 from NASA headquarters to execute it. And I think there's one other person in the room who was there, and that's Bill Barucki. Were you there, Jill? You were too? Okay, two. Okay. And I just thought I would give you this short story about how we got this thing started. So thank you very much, and a great pleasure to be here.
Thank you. Thank you, Dr. Worden. Hans Mark. It's now my pleasure to introduce our panel. Joining us here today is Natalie Battaglia, Kepler Deputy Science Team Lead from San Jose State University. William Barucki, Kepler Principal Investigator from NASA Ames Research Center. And Jill Tarter, Director of the Center for SETI Research at the SETI Institute in Mountain View, California. We're going to start with opening remarks and then take questions here at NASA Ames, followed by our phone bridge. Natalie?
Thanks, John. So before we get to the discovery, that you'll be hearing about, I'd like to share some other news with you. Our team has just finished combing through an additional quarter's worth of data to identify new planet candidates. And I'd like to share with you the results of that effort. We can start with the first slide that reminds us of what the objective of Kepler is. We've got a deliverable, a very specific task at hand, which is to determine the fraction of stars in our galaxy that harbor potentially habitable Earth-sized planets. And we must be mindful of that. And our strategies and our priorities are devised to accomplish that one goal. Since we've launched in 2009, we've released 2 catalogs of planet candidates. And the first one was in June of 2010, and it was based on 4 months' worth of data. So with this slide, I can communicate to you the results of that catalog by plotting the size of the planet candidate versus the orbital period on the x-axis. And some horizontal lines are added there for guidance to show you different reference points, the Earth, Neptune, and Jupiter. And in this June catalog, we had 312 candidates, and what was most noticeable about it is that most of those candidates were smaller than Neptune, suggesting that small planets are going to be common. After June, our next catalog release did not come until February of 2011. And that data analysis was based on 13 months of data. So we went from 4 months to 13 months. And it's no surprise, therefore, that the number of candidates increased significantly. So if I can have the next slide. We have the same plot here, but now we've added a group of red points which indicate the new candidates in that February 2011 catalog. And you can see with the counter on the bottom left-hand corner that the total number of candidates jumped from 312 up to 1,235, a really gigantic increase in the number of candidates. Of those 1,235, they're actually associated with 997 stars. And what that means is that 17% of these stars had multiple planet candidates. And that's turned out to be enormously important to us, enormously important for accomplishing our science objectives, because these multis are turning out to be very powerful systems for confirming the smallest planets. This data set also gave us our first habitable zone candidates, and so we were very pleased about that. And this is where we left off. Now, I'm going to present new candidates that have been identified in this additional quarter's worth of data. So what we've done now is we've gone from 13 months of data to 16 months of data. So we really haven't added that much data to the pool, to the mix, and we weren't quite sure what we would expect. What to expect. However, if I can have the next slide, the number of planet candidates has nearly doubled with this additional 3 months worth of data. You can see them here depicted by the yellow points with the counter in the bottom left-hand corner. This pool of yellow points represents 1,094 new planet candidates, bringing that total up to 2,326, and those are associated with 1,792 stars. So we still see this indication of lots of multiple systems, systems where the planets are flat enough in their orbits that you get multiple transiting signals from each of these successive planets. The percentage of multis was 17% in February, and now it's gone up a bit to 20%. We did have 170 stars with multiples, and now we've got 367, so the number's more than doubled. What you can see nicely in this plot with these different colors is how the parameter space is spreading as we collect more data. As you go from blue to red to yellow, you can see quite clearly that we're pushing down to smaller planets and longer orbital periods. And now we've got sizable numbers of candidates that are not just Earth-size, but actually below that Earth-size line. In the next slide, you can see the distribution of sizes, which speaks to the gains that we've seen, broken down by size. And so from the left to the right, we go from Earth size to super Earth size to the Neptune size, Jupiter size, and larger. Neptune size has a very large range of definition. It's from twice the size of Earth all the way up to 6, so it brackets Neptune. What you see in this chart, though, is that the increases are predominantly in the smaller planets. The number of Earth-sized candidates is now 207. If you remember, in February it was 68. So that represents over 200% increase in the number of Earth-sized candidates. Similarly, for the super Earth size, we've got an increase of over 100%, 136%. And you don't see that gain for the larger planets, 23% and 42% for the Jupiter and larger than Jupiter. And this is to be expected, right? Because as you collect more data, you gain sensitivity to the smaller signals because you average the noise down, you beat the noise down, and you tease out those very shallow signals. So we expected to see more Earth-sized planets. However, the reality is that we've also just gotten a lot better at this. We've had a lot of pipeline improvements that have facilitated the identification of these smaller planets, and I believe that the growth that we're seeing here is an indication of these more powerful pipeline modules and more powerful statistics for vetting out which are the true planet candidates and which are the false positives, and that's contributed to the success. In the next diagram, what I'm going to do is switch the x-axis, and instead of plotting the size against orbital period, I'm going to plot the size against equilibrium temperature. So this is the temperature you would expect to have on the surface of a planet being irradiated by a star at a certain distance. No consideration of atmosphere, just a simple equilibrium temperature. And plotted there for reference in the bottom left-hand corner is our Earth, who would have an equilibrium temperature of about 255 Kelvin, sitting there at 1 Earth radius. And as you go from the blue points to the red points to the yellow points in that bottom left-hand corner, you can see quite clearly that we are encroaching upon this parameter space occupied by our Earth. We are getting very close. We are really honing in on the true Earth-size habitable planets. Now, the green shaded region is marking the planet candidates that span equilibrium temperatures of 223 degrees Kelvin to 373. That brackets a little bit below the freezing point of water up to the vapor point, the boiling point of water. And this was our definition of the habitable zone back in February. And by this definition, we had 54 planet candidates, if you remember. The thing is that with the discovery of more and more habitable planets, scientists are becoming more discerning about what constitutes habitability. And recognizing that water's not going to exist on the surface of a planet if you have no atmosphere, right? You have to have an atmosphere. You have to have some pressure. And any atmosphere that you have is going to work to warm the planet, is going to have a greenhouse effect, right? So this changes the zone of habitability, right? It's going to push out the Goldilocks zone. So if we think about that and recognize that, we can change our criterion for habitability by moving the equilibrium temperature zone. And so the next chart shows you the temperature range that we're considering. It's 185 Kelvin to 303. And if you toggle back and forth between the previous slide and this slide, you can see how that zone is not only moving to the left to lower equilibrium temperatures, it's also narrowed a bit. So our definition of habitability has become more discerning. And with this new definition, we've got 48 planets in this habitable zone. And if you were to apply the same criterion to the February catalog, we would have seen 25. So that's just a point of reference. So what I'd like to do now is zoom in on this green region in the next slide to show you the candidates that are in this Goldilocks zone. You can see it bracketed by the dashed vertical lines, one on the left and one on the right. And in the middle, you have the dashed vertical line corresponding to the equilibrium temperature of the Earth. All right? And the Earth is plotted there for reference. So in this plot, you can see that, well, it's not obvious, but we have 10 planet candidates now that are near Earth-sized in the habitable zone. And by near Earth-sized, I mean 2 Earth radii and smaller. And you can see that those are predominantly the yellow points. These are our newest planet candidates, which makes sense because we're now more sensitive. Now that we've collected more data, we're more sensitive to also the longer period candidates. And so we've picked up some of those. Now, I'd like to point out one piece of information. If you go to the next slide, I'm going to superimpose these 5 arrows. 5 of these stars that are amongst these 10 have surface gravities in the Kepler input catalog, which is our catalog of stellar parameters that we use to characterize these planet candidates. They have surface gravities that seem a bit too high to us. There are systematic errors in the stellar parameters, in some of them, that lead to higher surface gravities systematically. And we use those surface gravities to estimate the radius of the star. And the radius of the planet is measured relative to the star. So for these 5 candidates, we have no better observation to tell us what that surface gravity should be. But yet inspecting the value that we have in our Kepler input catalog leads me to believe that they're slightly underestimated. And so for 5 of those candidates, I expect those systematic errors to push the radius and the equilibrium temperature up to the right, upper right-hand side of that diagram. I can't yet say how that's going to affect the parameters exactly, but I'm just introducing that as one caveat. Nevertheless, of these 10 candidates, we do still have 5 that are very, very high quality, robust candidates. Some of them are even members of multiple systems. So we believe that we've got some very, very viable candidates here that are Earth-sized, near Earth-sized, and in the habitable zone. And to illustrate that, I'm going to turn it over to William Barucki here, who's going to give you an example.
Thank you, Natalie. I'm William Barucki, the principal investigator of the Kepler mission, and today I have the privilege of announcing the discovery of Kepler's first planet in the habitable zone of a Sun-like star, Kepler 22b. It's 2.4 times the size of the Earth. It's in an orbital period of 290 days, a little bit shorter than that of the Earth. It's a little bit closer to its star than Earth is to the Sun, about 15% closer. But the star is a little bit dimmer. It's a little bit lower in temperature, 220 degrees lower in temperature. It's a little bit smaller. So that means that that planet, Kepler 22b, has a rather similar temperature to that of the Earth. The Earth's radiative temperature that Natalie mentioned is 255 degrees Kelvin. This is 262 degrees Kelvin, some 7 degrees different. So if the greenhouse warming were similar on this planet and had a surface, its surface temperature would be something like 72 Fahrenheit, a very pleasant temperature here on Earth. The star is some 600 light years away, so it's not terribly far away, but not terribly close either. You can see the images here. The orbital periods are about the same size. You can see the star at the top is a little bit dimmer than the star at the bottom of the Sun. And you can see how the Earth compares to Kepler 22b. What I'd like to talk about next is the data that made this discovery possible. Could I have the next figure? What we see at the top here is the Kepler's light curve. And the light curve is simply the brightness of the star as a function of time. So you see the variation of the brightness of that over 700 days of observations. Now, much of the drifts and jumps and things like that are due to the measurement errors that we have, and we need to take that out, correct the drifts, correct the jumps, and what our analysis pipeline does is produce the curve below it. If, on the other hand, we start and we look at the upper curve, you see there's 3 triangles. The 3 triangles are pointing out where the 3 transits that are required for confirmation occurred. And if you look, you can't really see the first event. The second event is that tiny little tick. The third event is another tiny little tick. And so it's nearly impossible to see that by eye unless somebody tells you. But when you take the data and you put it through the data analysis pipeline, what you end up with is that lower panel, and it's very clear. The transits are marked. They're very, very clear here. We've magnified the observations. The black areas are areas where the spacecraft did not take data. It turned toward the Earth, sent the data back to us, and a large one to the right-hand side is where the spacecraft was in safe mode, again, not taking data. But what's special here, what's really special, is to notice the first triangle occurs just a few days after we leave commissioning and we go into science operations. So we picked up the first of the 3 necessary transits. The second one is pretty obvious. The third one occurs just before this period of about 2 weeks where the spacecraft was not taking data again. It was in safe mode. That occurred just before Christmas of 2010. And we had this wonderful fortune then to find these 3 transits where, had there been any change when they occurred, we would have missed them. We would not be declaring the Kepler 22 as our first planet in habitable zone. So it's a great gift, and we consider this sort of our Christmas planet. So let's go on to the next figure. Here we've taken those 3 transits. We've added them together so you can really clearly see that transit. So you see the dip. You see how well it's defined. The depth of that dip is telling you the size of the planet. The size of the planet is 2.4 radius of the Earth. It's not 2.5, it's not 2.6, it's 2.4, just a smidgen above and below that. The period is something like 7.4 hours, and what's especially interesting are the dots above that. The dots above that are measurements we took not when the transit's occurring, but half an orbital period later. And that's the time where the planet's not going in front of the star, it's going behind the star. And so, since the planet typically it gives off about a billionth the light of a star, you shouldn't see any difference. And you don't see any difference. If you saw a decrease, it would mean it wasn't a planet that we were seeing, it was a star, because its light would be occulted. So, great confirmation, it's a planet, not a little star. On the right-hand side is another independent measurement. This is done by the Spitzer telescope, which is also in orbit around the Sun, like the Kepler telescope. But the Spitzer telescope looks in the infrared portion of the spectrum. Kepler looks in the visible portion. And if it's a planet, the depths of both transits should be essentially the same with an experimental error. And if we look, we see they are. The white curve is the curve from Spitzer, the red curve, that from Kepler. And the agreement is beautiful compared to the measurement error. So another wonderful confirmation. It is a planet. It is not some other astrophysical phenomenon. Could I have the next figure, please? What we're going to talk about here is what we'd like to be able to get at is the composition of this planet. To get a clue of the composition, you need the size and you need the density. The density you get from the size and a measurement of the mass. We don't yet have a measurement of the mass. Kepler measures size, not mass. But with our colleagues, we can sometimes get the mass with ground-based measurements. So let's look at what we have, what we can learn from what we have at currently. Vertical axis is the size of the planet relative to the size of the Earth. The horizontal axis is the mass that we measure for that planet. Lower left, we see Earth and Venus. Upper right, we see Uranus and Neptune, 2 of the larger planets in our solar system. And then we see we see a yellow band, which represents the size of Kepler 22b, but we don't know where Kepler 22b lies on that band because we don't have the mass yet. But when we look at the other curves, we see the white curve that goes from the Earth up to the right. And that is, if you took more rocks, more material that Earth is made out of, and you kept adding it to the Earth would grow in size, it would grow in mass, and would fall along that curve. If instead we had a planet that was essentially water and ice, that would be the dashed curve. And its density is less, so it's above the curve of Earth, which is mostly rock and iron. And so we would see it grow, and it would cross that yellow curve, the yellow band for Kepler 22, as it got more and more mass toward the mass of 20. If we talked about planets that had lots of hydrogen and helium, when you add those gases, they're very expansive, and so the atmosphere becomes very large, and we see planets like Uranus and Neptune. So 10% hydrogen helium, the lower white curve, solid curve. 20%, a curve somewhat above Uranus and Neptune. It's clear from the yellow band that's not where Kepler 22 lies. It lies somewhere between Earth composition, so you would expect it to have a lot of rocky material, And it probably has a lot of water as well. This coming summer, we will have an opportunity to try to measure that mass because the star will be high in the sky, and the telescopes, the ground-based telescopes like Keck and possibly HARPS North, will be able to at least attempt to get the mass of this planet. And I believe they have a good chance of being successful, and they will know where this planet lies on that curve. Clearly, it lies in an area which hasn't been explored. We have no planets like this in our solar system, things that lie between the Earth and Uranus and Neptune. So that will be a wonderful part of our discovery. So let's go to the last figure. In this figure, we've plotted not only the Earth there in the center at 255 Kelvin, but our discovery, Kepler 22b, which is fairly close. We've also plotted all the many other candidate planets. Most of these candidate planets, I think, will turn out to be real planets. And what we're seeing are some 48 objects, planetary candidates, in the habitable zone between 185 and 303 degrees Kelvin. It's conceivable that any or many of these planets and planetary candidates and their moons could have life. And clearly, they are good targets for a SETI search. And Jill Tarter is here to tell us about the SETI search. Jill?
Thank you, Bill. I'm Jill Tarter, the director of the Center for SETI Research at the SETI Institute down the road. My team is interested in using the results of Kepler to find true Earth analogs. According to Carl Sagan and his colleagues in their 1993 Nature paper titled A Search for Life on Earth from the Galileo Spacecraft, one of the strongest pieces of evidence for life, indeed intelligent life on Earth, was the presence of narrowband pulsed amplitude modulated radio transmissions. While there may be some uncertainty about exactly how to define the habitable zone, an exoplanet that could be detected through the technosignatures of its inhabitants would surely qualify as an Earth analog. At the SETI Institute, we've begun using the Allen Telescope Array, a radio telescope currently composed of 42 6-meter antennas. We've used it since last January to look for technosignatures from the Kepler worlds. The Allen Telescope Array is located in rural Hat Creek Valley in Northern California, away from the transmitters that accompany large populations. Last April, we had to interrupt our exploration of the Kepler worlds when the antennas were put into hibernation mode due to a lack of operating funds. But I'm really pleased to announce that as of 6:18 this morning, when the Kepler field rose over the observatory, the ATA was back on the air, continuing the search for Earth analogs. This restart of observing was made possible by the generosity of the public, who responded to our SETIstars.org website, and to funding from the U.S. Air Force as it assesses the utility of the ATA to assist in its important space situational awareness mission. Because of the unique capabilities of the ATA, it's our intention to interrogate all 9 billion narrow radio channels that comprise the naturally quiet terrestrial microwave window running from 1 to 10 gigahertz in the spectrum. At lower frequencies, there's increasing noise from galactic synchrotron radiation, and at higher frequencies, our own atmosphere adds additional noise. Now, as a very small tribute to Professor Bob Rood, a University of Virginia astronomer who passed away on November 2nd, we're resuming our exploration at the high-frequency end of this quiet window. We're focusing on the 200 million radio channels that surround the emission line of the 3 helium-plus ion. This line's at 8.66 gigahertz, and it was suggested by Rood and Professor Tom Bania from Boston University as an obvious frequency for interstellar communications. It's the simplest spin-flip transition after the 21-centimeter hydrogen line that most people are familiar with. This is an emission that occurs when the spin of the electron orbiting the nucleus shifts from one direction to the other, and an emission at radio frequencies results. Rood and Bania argued that radio astronomers on other worlds might be more tolerant of transmitters operating at this higher frequency, thus keeping their skies quiet for the study of hydrogen, the most abundant element in the universe. This is a largely unexplored frequency region for SETI. And if it doesn't yield evidence of extraterrestrial technologies, then we'll go on to study the rest of the microwave window. And what might a technosignature look like? Well, perhaps an Earth analog might look like the planet Mars did when we observed it just before Thanksgiving. Both the Mars Reconnaissance Orbiter and the Mars Express spacecraft happened to be transiting the planet, and their carrier signals were clearly visible. Now, extraterrestrial transmitters must be a lot stronger than these to be visible over interstellar distances as opposed to interplanetary distances. But we won't know if they're there unless we look. So as of this morning, we're once again looking at all the Kepler exoplanet candidates. And as of tomorrow morning, our catalog will be twice as big. But just like Jodie Foster and her contact pushpins, we will give a higher priority to those worlds that our colleagues tell us are not too warm, not too cold, but just right. So federal and institutional funding have brought us to this really exciting threshold. Astrobiologists will examine these exoplanets for signs of biosignatures. But at the SETI Institute, we're going to carry forward the public's quest for technosignatures and the ultimate Earth analog as long as the public continues to support our efforts on humanity's behalf.
Thank you, Jill. We'll now take questions here at NASA's Ames Research Center, followed by our phone bridge. Remember, if you have a question here, state your full name and affiliation. We'll start with Irene.
Hi, yeah, it's on. Eric Ham with Nature Magazine. I want to make sure I understand the statistics you just gave us, Natalie. 48 in the habitable zone, but there's also 207 Earth-sized candidates. What's the Venn diagram of those? Was that the 10 that you're talking about?
That's the 10 that I'm talking. Well,
because I thought your category for
no,
Earth
no,
is
no.
even smaller than less than 2. I thought it's 1.25.
Our definition of Earth size is 1.25 and smaller. So you're asking, is there an intersection between that 207 and the ones that are 185 to 303? And I want to say that there's one, but it happens to be one of those that has this anomalously high surface gravity. So I'm not sure how it's going to play out. As soon as Cygnus gets back up in the sky, we'll be observing these candidates to pin down their stellar properties more accurately and see evaluate those new radii.
And if I can follow up with one more, this planet that you've confirmed, you had the 3 Kepler signals exactly a year ago. And presumably you tried to follow up with ground-based observations this past summer, but you didn't seem to imply that worked or not. So what was it that allowed you to say, okay, this is a confirmed planet?
Well, there's quite a few different tests that we do, and I'll be talking about those a little bit later. But one of the things that we did was we made 16 measurements with the Keck telescope, and that allowed us to say the mass couldn't be greater than a certain value, something 1 sigma, 36 times the mass of the Earth. The measurements were made when the planet was going through a node, and it'll be going through a loop this summer. That is to say, the amplitudes will be very high of the radial velocity. So we're talking about a radial velocity measurement that we'll be making in the summertime. The ones that we made earlier basically told us that the mass couldn't be higher than 36 times the mass of the Earth. 3 sigma was something like 126 times the mass of the Earth. These values are so low that it can't possibly be a star. We're clearly seeing a signal, and the radial velocity is saying it cannot be a star, it must be a planet.
There were also the Spitzer observations that we took, And then the astroseismology, too. I mean, there were several pieces to the puzzle that had to all come together to confirm this and really understand and know that it is an object, a bona fide planet in the habitable zone. And it just takes time.
Yeah.
Hi, I'm Irene Klotz with Reuters and Discovery News. I guess it's kind of the same question from the other side of the coin. The if you discard the 5 stars that you think there's some
Discard.
okay, let's just say
They're
set
just gonna
aside.
move around
okay,
a
just
little,
set aside
that's all.
for a
Yeah.
moment those 5 and
Yeah.
the remaining 4. What's missing from the other 4 candidates that you could that's like awaiting confirmation? Is it this issue of that the telescope happened to be in safe mode, so you weren't able to get this ding ding ding, or what else?
Yeah, no,
needs
that's a
to
really
happen?
good question.
Thanks.
The transits are clear. They're very high quality candidates. What we want to do now is the series of follow-up observations that we would give, the attention we would give to these candidates, like we did for Kepler 22. That was a good example. We want to observe the star and understand its properties very, very well. We want to do some radial velocity work so that we know that it's not a false positive. We want to just apply all the different criteria that help us to weed out any probability that it might be a false positive before we have confidence in the planet interpretation. So that's what's lacking.
And also, I wanted to know what you mentioned that when you find the multiple planetary systems, that it's helpful for homing in on smaller planets. How does that work? Are you seeing like wobbles in signal that you think, oh, I need to, do a little more research on this? And also, can you just kind of paint a family picture of the 22, Kepler 22?
The multis have been important for 2 reasons. One is because if you've got one candidate orbiting a star, you have a certain probability that it might be something else, some astrophysical false positive. But if you have 2, and that probability is very low. Now, if you've got 2 planet candidates, the probability of having 2 false positives is ridiculously small. So when you see multiple planet signatures in your data, that increases our confidence substantially that that the planet interpretation is the right one. So that's one thing. The other reason why the multis have become important is because we are measuring the timing of the transits. And in many cases, they are not perfectly periodic. They should be if they obey Kepler's laws, right? Because they orbit, they've got a certain orbital period, and they reoccur at this beating, right? But what we observe in many cases is sometimes the transits arrive a little too soon, a little sooner still, and then they start to catch up, and then they're a little bit too late, and they're doing that because neighboring planets are tugging on one another, and they're exchanging gravitational energy. And in doing so, and that exchange is strong when you have resonances, for example. If the outer planet orbits once for every twice that the other planet orbits. And it's a very powerful technique for backing out the masses of the planets. So we're finding that that's much more powerful than we expected it to be. We're finding it's going to be very, very helpful to us.
Govert Schilling, freelance from the Netherlands. 2 very simple questions, I guess. The first one, is Kepler 22b in the constellation of Cygnus, or is it in Lyra? And the other one is, are there any indications of this star harboring multiple planets?
I don't know the answer to your first one. I don't know whether this is technically in the Cygnus constellation or Lyra, because they, of course, butt one another. So I don't know the answer to that.
We'll find out
but,
for you.
Right. Your second question, what was your second question?
If it's multi. If
multi.
there's any indication.
We've looked very hard to see if we can see any transit timing variations. And we don't see them at this point, but we only have 3 transits. Actually, in the last several months, we have seen transit number 4, and we will see transit number 5 this coming year. So we'll have 5 transits. The timing variations that you need to measure, we'll get a much better measurement for. But we have no evidence at this point for another planet.
Oh, yeah. Hi, Mike Wall from space.com. So you're saying, just in the last 3 months, or an additional 3 months after the last data release, you got more than 1,000 new candidates. Do you anticipate that as you get better and better at this, these finds are going to just keep piling up, or I mean, where are you going to plateau?
Yeah, that's a great question. I think that we're going to have at least one more batch that's going to be a market increase. And I say that because I know that there are pipeline improvements coming down the pike here that are going to help us to identify the small transits. And so what happens is we have these things, for example, called sudden pixel sensitivity dropouts. It's an instrumental effect that causes the brightness to appear to deviate. And we can correct for it. But with our current pipeline, we can't correct for it perfectly or in all cases. And so sometimes what happens is the pipeline recognizes that little deviation as a transit. And it keys off on that, thinks you have a planet signal, and then it doesn't filter it out properly because it can't, because it doesn't look like a real transit, to go back and search for real transits that might be there. So we would miss them if they're there. So we've already designed software that's going to improve that significantly, and that's going to allow us to get rid of these sudden pixel sensitivity dropouts and find the smaller planets. And I think that's one example. And I think that that's going to give us another big haul this next time. But I hate to predict, but that's what I would garner.
Oh, Dennis Overby, New York Times. Just one small dumb point, because I get confused by all these numbers. Me too. So there were 10 Earth-sized planets in habitable zone,
We
which
call
you then
them near Earth size, so smaller
near
than
Earth size. So
smaller than, well, we're including the super Earths.
so you are, so 22b is one of those.
22b is slightly larger than 2. So it's,
that's not one of the 10.
It's not one of the 10.
Okay,
no, but it's close.
That's all. All right.
Yeah. Our definition of super Earth is kind of, I mean, it's not completely arbitrary, but we have to draw the line someplace. And so super Earth ranges from 1.25 to 2 Earth radii. But, you know, we don't know anything about the planets between Earth size and Neptune size, because in our own solar system we have no examples of such planets, right? So between 1 Earth radius and 4 Earth radius, there's nothing. So we don't know what their compositions are going to be. We don't know what fraction are going to be rocky, what fraction are going to be water worlds, what fraction are ice worlds. We have no idea. Until we measure their densities and get some statistics, we just don't know. So we put the line at 2, we draw the line in the sand at 2, and Kepler 22 is a little bit larger.
Okay, great.
Hi, I'm Dennis Ebbets from Ball Aerospace in Boulder. Natalie, your number of 1,792 stars that show evidence of planets is extremely interesting. You're monitoring about 150,000 stars, and that suggests that more than 1% of the stars that you're monitoring show evidence of planets. And if I remember right, 1% was kind of the geometrical probability of there being a transit. That suggests, you know, you're exceeding that. So it sounds suspiciously like almost every star might have some kind of a planetary system.
Yeah,
A to something is 1.
That 1% is for a certain orbital period.
Right.
So if you have very short period objects, and many of ours are short period, the probability of having an alignment, having a transit is higher. It's more like 10%. So you'd multiply by 10, not 100. But yeah, point well taken. That'll be the next thing we do. This catalog that we are sharing with you today, and we literally finished like Friday morning at 4 a.m. or something crazy. We haven't had the time to look at it and now translate these numbers to actual statistics, to occurrence rates. That'll be the next thing that we'll do when we get back home.
Okay, we'll now go to our phone bridge. If you're on the phone and would like to ask a question, please remember to press *1 on your phone. We'll start with Dave Perlman with the San Francisco Chronicle. David, go ahead.
Oh, thanks very much, if I'm on. For Natalie or Bill, define the criteria that turns a candidate into a confirmed planet in terms that, you know, readers can understand.
Well, basically, we look at a series of measurements, active optics, speckle, make a series of measurements. We do a modeling of the size of the star, the size of the planet, how the signal looks like when the planet crosses the star, how round that is. And we put this into a model and come up with the likelihood that it's a planet. We calculate for the planet, the probability it's a planet. We calculate as well the probability that it's a false positive. That's a binary star. And so we look at the odds. What are the odds that it's a planet compared to the odds that it's a false positive? And when that number is something in the order of 100 or to 1,000, then we say we've made all the measurements that rule out everything we know about. The odds are greatly in favor of it being a planet. The Kepler science team basically looks at this and decides together, are we willing to defend this as a planet? If the answer is yes, then we have marshaled all the evidence. We submit this as a paper to a professional journal, and we have outside experts look at what we have provided in terms of evidence. And if they say yes, the paper's accepted, we say indeed we will declare this, announce this as a planet.
We have kind of a three-pronged approach. I mean, three different approaches that lead to confirmation. One is radial velocity, right? Doppler detection, traditional. The other is transit timing variations, which I described earlier. The problem is that for the smallest planets, those two methods don't always work. So the third approach is to say, okay, let's make a list of every astrophysical thing that this could be other than a planet. And let's just tick them off one by one. Let's take a series of observations and ask ourselves the question, is this scenario consistent with what I observe? And you're essentially eliminating all the other possibilities that it could be. And of course, you can't eliminate all of them. But if you can eliminate almost all of them to the point where the probability of it being an astrophysical false positive is so ridiculously small, then you say, yes, we have confidence that the planet interpretation is right, because the probability that it's a planet is orders of magnitude higher than the probability it's an astrophysical false positive. So those are the three basic techniques that we use to lead a planet candidate to confirmation.
Okay, we'll now go to Seth Bornstein with the Associated Press.
Which was just on the edge of the habitable zone. Can you compare this to that? Is this more habitable, more human type habitable than that? And how how many light years are we talking from Earth?
Seth, could you repeat your question? I don't think we heard the top of it.
Yeah, compared to what?
In September, HARPS announced confirmation of HD 85512b. It was in the constellation Vela. It was through the people over at HARPS did that in the habitable zone, but barely. It was a 3.6 mass Earth at 85 to 100 degrees, 120 degrees Fahrenheit, a rather hot, steamy one. So I'm wondering, how does this compare to that one? And can you just sort of paint a picture? This sounds a lot more comfortable, Bill. You talked about it as a pleasant 72 degrees. From what we know, what is a picture? What would it be like on this versus what we know about other planets in the habitable zone?
One of the concerns, of course, is that as you warm up a planet and get the temperature higher, you get much more evaporation of the water. The water becomes a larger portion of the atmosphere. At some point, the water enters the stratosphere and you start losing it from the planet altogether. So the concern is you can't really heat a planet up very high before you start losing all the water. And so I don't know what the situation is there. And another aspect of that is I don't believe they got a transit. They got a mass, but not a size. And so you don't know whether this is a gas giant or just what it is. So there's a lot of unknowns here. I suspect that the planet that we have found is probably, there's a good chance that it could be rocky. I expect that the planet we're talking about, on the Vela planet, could also be rocky, or at least have a lot of rocky material. But I don't know that we can tell you much more about which one would be more habitable. But I would certainly like to have a lower temperature rather than a higher temperature, because of the evaporation of the water into the atmosphere.
I think Bill already said this earlier, but let me just reemphasize the point. I think there's two things that are really exciting about Kepler 22b. One is that it's right in the middle of this habitable zone, right next to Earth. So it's not at either edge, and the other two are kind of, they bracket that, they're at either edge. The second thing that's really exciting is that it's orbiting a star very, very similar to our own sun. Whereas 85512 and Gliese 581 are cooler stars, K and M type stars. This is a solar analog. It's almost a solar twin. It's very similar to our own sun, and you've got a planet twice, 2.4 times the size of the Earth, right smack in the middle of the habitable zone. So I find it very compelling for those two reasons.
Thanks. We'll now go to Kelly Beatty with Sky and Telescope. Kelly?
Thanks very much. Two quick ones for Jill. I hope they're quick. First is, how long is the funding for ATA assured? And the second question is, the Drake equation has a factor for the number of stars that are thought to have planets. Is there some side bet somewhere between you and the Kepler project on what that number will ultimately turn out to be?
Well, we're not betting. We're just trying to look at everything that Kepler has provided as a candidate. Because remember, although Kepler may have found larger short-period planets that don't necessarily look to be particularly habitable, there may yet be other planets in that planetary system to be discovered with longer periods. So planetary systems are a good place to look, and Kepler is providing us with a wonderful set of targets. So we're just taking everything we can get from our Kepler colleagues. And in terms of, Kelly, I've forgotten your first question. Oh, funding. Yes, how can I forget about funding? We're good for the short term. We are in negotiations for a longer term contract. It hasn't come through yet, but we're very hopeful. But we're going to need to have continued public support in addition to finding partners to keep the array operational. Our SETI work has to be funded by the public, and so that's going to be an ongoing obligation.
Thank you. We'll now go to Camille Carlisle with Sky and Telescope magazine. Camille?
I actually just have a clarification question. I'm not sure if I heard it correctly. For Dr. Baruki, did you say the planet's period is 7.4 hours?
No, I think you've misunderstood that. The planetary's period is 290 days, or to be exact, 289.9 days. Somewhat similar to that of the Earth, a little bit shorter. The duration of the transit, when the star is being dimmed by the planet crossing it, is 7.4 hours. I think that's where you got the 7.4.
Right. Thank you.
Thank you. If you have a question on the phone bridge, please remember to press star 1 on your telephone. We'll now take another question from Dave Perlman with San Francisco Chronicle.
Oh, thanks again. My phone went dead at the right time or wrong time. I'm trying to understand whether there was a press release from Caltech, and it said that it has found 18 new planets confirmed around stars more massive than the sun. Are those numbers included in today's announcements?
No. What you've just said is actually news to me. I haven't heard that yet. They're probably talking about it right now in the conference, and we're not there.
Planets, but they are confirming them.
Yeah.
And
I did see a preprint that was posted to Astro PH, the archive, about a week ago with one orbiting an M dwarf. But this is news. So did that just come out today?
No, as a matter of fact, it came out on Friday.
Okay.
And I was in the office over the weekend and
well, the Caltech team is not the only other team that's confirming Kepler candidates. The Europeans have also been very active, actively working on confirming our candidates using the SOPHIE spectrograph, for example, at the Observatoire Provence. They've already confirmed 2 that are published, and they've got another batch that are on the preprint servers, so those will be, I'm sure, in the published literature soon. So we're just thrilled about this. We need all telescopes observing these candidates so we can confirm as many as possible, understand what our false positive rate is, because that's going to increase our the reliability of the determination of what we call Eta Earth, right? The fraction of stars that harbor these Earth-like planets. So this is great.
Well, and if I may follow, I had a question for Jill, and that relates to the broadcast frequency that you are going to zero in on. Was it Kepler 22b or just all the Keplers?
No, that's those are the set of frequencies that we're looking at to start our search of the terrestrial microwave window. So we're looking around 8.66 gigahertz, and that will take us a few days, actually twice that now, since we have twice as many candidates to go through, and then we'll start back where we left off in the spring, down at the lower frequencies.
Hey, David, let me just clarify one thing. Maybe I didn't appreciate your question. You asked if their new confirmations were included in our count, and I'm not exactly sure what you mean by that, but certainly these candidates that they've confirmed are probably drawn from our February catalog. But they would not be amongst, they would not necessarily be amongst the new planet candidates because we haven't yet made those publicly available.
Thanks. I think we have time for a couple more questions. We have two on the phone bridge. Follow-up from Seth Borenstein with the Associated Press.
Thanks. I just wanted to, if Bill or Natalie, if you can, or even Jill, if you can just push a little harder on what I'm trying to get the sense of, is it fair to say that this is the best target right now that we know of for the possibility of life elsewhere, and why? I mean, I have editors who just still don't understand that this is a story, and if you tell me how big a leap it is to get something so smack in the middle of the habitable zone.
I think it's critically important to do that. We're finally looking at the planets in the habitable zone, or the candidates in the habitable zone, and we're confirming them. They're not false positives. They're not going to be substantially warmer or colder. We have now got good planet confirmation with Kepler 22b. We're certain that it is in the habitable zone. It's not at the edge. And if it has a surface, it ought to have a nice temperature.
One more on the telephone from Kelly Beatty with Sky and Telescope.
Thanks very much. This is also for Bill Barucki. Bill, the situation with Kepler is such that the stars are a little bit noisier than you thought, and you're actually going to need more time to study these in order to get the pipeline such that you'll find all the candidates you'd like to in the habitable zone. Can you give us an update on where you think things stand with getting a mission extension? I think you have a review coming up very shortly.
Yes, there'll be a senior review coming up I believe in February. We're putting together a very good proposal, pointing out that the stars that we have been measuring, the G stars like the Sun, have turned out to be quite a bit more variable than anyone expected, and that makes it much more difficult to find small planets, which are of most interest to us, particularly small planets in the habitable zone. And so the only way that can be done is to get more transits. So instead of 3 transits, if we can get 6 or 8 transits, that would dramatically help us find these small planets. And so we're asking the senior review to entertain our proposal and to continue the mission from 3.5 years is what we have now to something of the order of 6 years or something like that to get these additional transits.
Okay, we're going to come back here to see if there's any follow-up questions in the room. Irene?
Thanks. I realize that there aren't any biologists on this panel, but I'm sure in your off hours you must speculate this a little bit about, aside from having a planet the right size and in the right place, what else would be needed to have there be something beyond microbial life on it?
That's a good question. I think Jill is probably the best one to answer that.
The answers to that question range all over the map, Irene. There are people who have this rare Earth hypothesis that there are so many special things about Earth, including having a Jupiter at 5 AU when you have an Earth at 1 AU, having the magnetic field strength that we have, having et cetera, et cetera, et cetera. But we have an example of one. In a physics experiment, when there are multiple outcomes, you want to run that experiment many times and figure out what the branching ratios are. How many times does it end up in this way? How many times does it end up in that way? We haven't been able to do those experiments yet. We don't know whether the Earth as it is and life as we know it here is if the way we got here was very unusual, that elsewhere things go in a different way. It makes it much easier. Or are we common? I mean, that seems to be the only appropriate way to treat a statistic of one is as a median, right? We're average. We just don't know that. And we can have a lot of discussions, and certainly extremophiles are opening our eyes about, for microbial life and actually some macroscopic life, the conditions that can be quite comfortable for different forms of life other than human. So this is a work in progress. We just don't know. We wish. In this field, number 2 is the all-important number because we count 1, 2, infinity, right? As soon as we find a different, a separate, an independent example of life somewhere else, we're going to know that it's ubiquitous throughout the universe. So we're all looking for number 2.
Thanks. We'll take one more question and then we'll conclude today's news conference.
So this new catalog, the candidates are now out there as of today?
No, it's the catalog's been under review for the last week with the science team. And so once this conference is over, we'll go back to our computers, get it in a form that the public can digest, and then release it. So I'm guessing another 2 or 3 weeks, and then it'll be publicly available.
I guess the reason I ask, I mean, so this is, I believe, the 27th planet confirmed by the team in total? Kepler now has 27?
I think it's 28.
By the Kepler team, yes.
29.
Yes, that's correct.
You're also announcing, that you have over 2,000 candidates, right? So it's 2 orders of magnitude difference between the number of candidates you have and the number that you've been able to confirm. It seems like you're drowning and you desperately need help here. Are you considering turning them loose earlier so that, all these other folks that have more telescope time can start independently confirming?
Yeah, well, we do already have 1,235 of them out there, so we're still talking orders of magnitude. But yeah, absolutely. I'll be talking a little bit about that in my talk at the conference. Our plans for releasing data so that when they do confirm planets, they can do an analysis that's more robust and pin down the planet properties more accurately. So we'll be releasing a lot of data coming up here in January. We'll have a big data release. But we don't hold up the catalogs by any means. We don't hold them back. As soon as they're ready, it'll be publicly available. So we're working literally around the clock to get this done as quickly as possible. It just takes time. It just takes the time that it takes.
And of course, you've seen the catalogs, earlier catalogs come out, and the fact that our colleagues throughout the world are already using that information to do confirmations. So we have asked for their help, and they are helping. So it's not just this group, but the whole world that's helping us confirm these planets.
That's absolutely right. There's never been somebody, an outside astronomer who has come to us, who has approached us and said, I want to help, that we've turned away. Everybody is engaged if they want to be. And we will increase that collaboration and coordination as we move hopefully into an extended mission. We will open up that so that everybody has access to all of the information at all of the time, but yet still try to coordinate it, because what we don't want are wasted resources. Time on these telescopes is extremely difficult to come by, and is extremely difficult to operate those telescopes. I mean, costly. You do not want people repeating efforts. We want to maximize the science yield, and the way to accomplish that is through cooperation.
Another aspect of that, of course, the public is looking at the data, and there's a group called Planet Hunters. And they have found planets that we haven't noticed as readily as they have, and they brought those to our attention. So there's a huge number of people. I think there have been millions of downloads of the data for people to look at.
Thank you, Natalie, William, and Jill. That concludes today's news briefing on Kepler. For more information on NASA's Kepler mission, please visit us on the web at www.nasa.gov/Kepler, where you'll also find today's slides. Thank you for joining us.